These are days of valuable discoveries in electrical science, of tremendous advances in radio. Designing, applying, and servicing electrical equipment are among the most vital jobs we have to do. An indispensable electrical device is the cathode ray tube, with its wide variety of practical engineering uses. The cathode ray tube is a device for producing a visual image upon a screen. In practical engineering laboratories, the cathode ray tube is used in an instrument called the oscilloscope. Here, it produces a graph which can be used to make a variety of delicate electrical measurements. In this film, we'll find out just what the cathode ray tube does and how it does it. Let's take the glass container off a typical tube and see what's inside. At the base of the tube is a filament. Fitting over the filament is the cathode, a cylinder coated with earth oxides. Around the cathode is a shield called the control grid. Next are two anodes. The first is the focusing anode, and the second is the accelerating anode. These parts of the tube make up what is called an electron gun because it shoots a beam of electrons at a screen. At the end of the tube is the screen. All these parts are enclosed in an evacuated glass envelope. Now to find out what each part does inside the tube. The filament is like the filament in any electric bulb. When current is passed through it, it gets hot and gives off light. The real purpose of the filament, however, is not to give off light, but to act as a heater for the cathode. When the cathode is heated by the filament, a swarm of negative electric particles called electrons is actually boiled off the surface of the cathode. The electrons remain in space until they are acted upon by other elements of the gun. The anode farthest from the cathode is called the accelerating anode. It is a metal cylinder which carries a high positive charge. And since unlike charges attract, the negative particles or electrons given off by the cathode are drawn to the anode at terrific speed. Since this accelerating anode is a hollow cylinder, some of the electrons rush through it and bombard the screen. The screen, the front inner surface of the tube, is a coating of fluorescent material that glows at the point where the stream of electrons strikes and excites it. So on the front of the screen, a round spot of light appears. The spot, however, is large and fuzzy. For practical purposes, we need a sharply defined spot. The focusing anode helps do this job by concentrating the stream of electrons into a small beam before it reaches the screen. The electrons converge and strike the face of the tube as a sharply focused spot. The grid controls the brightness of the spot. It carries a negative charge, and since like charges repel, its walls check the flow of electrons, while the opening in the center acts as a gate to allow some of the electrons to be drawn through by the anodes. If the negative charge on the grid is increased, fewer and fewer electrons are allowed to pass through. When the negative charge is reduced, more electrons are allowed to go through, and form a brighter spot on the screen. The grid, then, controls the intensity of the beam and the brightness of the spot. Just as the focusing anode controls the size and sharpness of the spot. We have seen how the electrons coming from the cathode are concentrated into a ray, and how the spot on the screen is created by the cathode ray from which the tube gets its name. Now let's see how the spot of light is controlled to produce a moving image on the front of the tube. There are several methods of moving the spot in the cathode ray tube. The first of these methods can be illustrated by a simple experiment with static electricity. For example, we can give a hard rubber comb a charge of static electricity. The negatively charged hard rubber comb will deflect the beam. As the comb is brought closer, the spot moves down, away from the comb, because like charges repel. As the comb is drawn away, the spot returns to its original position. In the same way, we can move the spot to one side of the screen or the other. Repelling the electron beam with a negatively charged medium is called electrostatic negative deflection. On the other hand, we can place a positive charge of static electricity on a glass rod by friction. Since unlike charges attract, the positively charged glass rod can be used to attract the beam. As the rod is moved downward, the beam moves up. It moves to the left or the right with the rod. We call this electrostatic positive deflection. In actual practice, electrically charged plates inside the tube serve as deflectors. Either a positive or negative charge can be placed on the plates. A positive charge attracts the beam, and a negative charge repels it. Positive, the spot moves up. Negative, the spot moves down. Here is a laboratory demonstration setup with individual controls which can be used to vary the voltages on the deflecting plates. Gradually increasing the positive charge on the top plate moves the spot upward. As the charge is reduced, the spot returns to the center of the screen. Two plates can be used, one with a negative charge, the other with a positive. Varying the voltage applied to either of the plates will move the spot. The spot moves farther with two forces simultaneously attracting and repelling. The horizontal deflection plates in combination have the same effect. The greater the charge on the plates, the farther the spot moves. Using all four plates in combination, we can move the spot in any direction on the screen. This electrostatic deflection of electrically charged plates is perhaps the simplest method of controlling the beam. Another method of moving the beam in the cathode ray tube is magnetic deflection. We all know that a sprinkling of iron filings will show a pattern of the lines of force about a bar magnet. We know also that the lines of force flow from the north to the south pole of the magnet. Now let's work on the beam with the bar magnet. First, with the north pole of the magnet toward the tube. Note that the spot moves at right angles to the magnetic field as the magnet approaches the beam. In accordance with basic electrical laws, the deflection is at right angles to the lines of force. As the magnet is drawn upward, the spot moves back horizontally across the screen. As it is lowered, the spot moves outward, in and out, always at right angles to the position of the magnetic lines of force. The south pole of the magnet deflects the beam in the same manner, but in the opposite direction. No matter how we hold the magnet, the direction of the spot movement is always at right angles to the magnetic field. An electromagnet will give more practical control over the movement of the spot. Here is an experimental setup with electromagnets placed around the tube where they can pull or push the spot from all sides. Each coil is connected to a rheostat so that the amount and direction of flow of current that passes through it can be controlled. So, by passing a small amount of current in one direction through the top coil, we attract the beam. We can help move the spot by passing a current in the opposite direction through the lower coil, so that its field will repel the beam, push it away. The more current passed through the coils, the stronger the fields and the farther the spot moves away from the center of the screen. Now let's try putting varying currents into both sets of coils at once. With the currents continuing to increase on both the top and side coils, the attraction is increased in two directions at once, and the spot moves diagonally. By varying the currents in the coils, we can move the spot any place on the screen. Now, here is an important point. If the spot is moved back and forth rapidly over the same path, our eyes will see a solid line instead of the moving spot. Let's see what happens when we vary the currents in all the deflecting coils simultaneously. When the crank is turned on this mechanical device, the varying currents in the vertical and horizontal coils are synchronized to show us how the spot is moved by a pulsating direct current. Likewise, with the same arrangement, we can change the direction of flow in the vertical deflecting coils to show how the spot is deflected by an alternating current. In this film, we have learned how a cathode ray tube produces a spot of light upon the screen. We've seen the various methods of controlling that spot, electrostatically and electromagnetically, to produce a changing pattern of light. Here, for example, the cathode ray tube shows us an actual picture of the voice vibrations you are hearing at this moment. Because the beam was argued, the moment that thing here is in the share about self-reverse, if blues happens as those blues here go like it. Wolf has girl free. Here, for example, the cathode ray tube shows us an actual picture of the voice vibrations you are hearing at this moment. Because the beam of the cathode ray tube responds instantly to the most rapid voltage changes, it can be used to produce the characteristic patterns of almost any type of fluctuating current, from the simple to the complex.